drivers lose sight of land out here, both sides gone for miles. Just water, sky, and a thin road. 24 miles of open water. Workers built almost every foot of it above the lake itself. No shortcuts, no detours around the middle. Just straight across, mile after mile. Getting to the other shore used to take hours by car. Quick question before we start. Where are you watching from today? Getting across this lake used to take hours. One idea from 1948 changed that completely. After World War II, New Orleans grew fast. New families needed places to live. Many settled north across Lake Pontchartrain from the city. One problem stood in the way. The lake itself blocked any direct route north. Drivers had to circle around it. That detour added serious time to every single trip. Hours, some days, just commuting. Business leaders noticed this problem too. Growth on both shores felt limited. A direct crossing could change that completely, but nobody had built one yet. In 1948, a man named Ernest Lowettway had an idea: build a bridge straight across. Lowettway looked at similar projects elsewhere for inspiration. Biscayne Bay in Florida offered one example. The Zuiderzee project in Holland offered another. Both crossed open water directly. Lowe believed Lake Pontchartrain could support something similar. He just needed support behind it. He began lobbying state lawmakers immediately. Convincing them wouldn't happen overnight, though. Louisiana's legislature eventually agreed to consider it. They put the question before voters. That same year, in November, voters approved a bond issue, $30 million authorized for construction. This approval created real momentum for the project. The legislature then formed the Causeway Commission. This commission would oversee everything moving forward: planning, funding, eventually actual construction work. Still, years passed before real building began. Bureaucracy, funding details, engineering questions all needed solving. The Louisiana Bridge Company formed in 1955. James Walters became the project's director. Ernest Lowettway stayed closely involved throughout this process. His nephew helped with planning too. By this point, expectations had grown considerably. This needed to be genuinely ambitious. Not just a bridge, but the longest bridge over water anywhere. Nobody had attempted anything quite like this before. 24 miles, almost entirely over open water. Existing bridge building methods simply weren't built for this scale. Something new would be required. Engineers needed a way to work fast. Waterborne construction across an entire lake, whatever method they chose, needed serious efficiency behind it. Time and money both mattered enormously. The contract eventually signed reflected this urgency directly. 23 months for the entire crossing. That timeline seemed almost impossible for a project this size, yet everyone involved committed anyway. Getting the idea approved took 7 years. Actually building it would move much faster. Approving the bridge was one vote. Building 24 miles of it fast was a completely different challenge. Construction officially began in May 1955. Workers drove the very first piles. The contract demanded something genuinely aggressive: 23 months for the full 24 miles. Engineers Upson and Blessey led the design work. Palmer and Baker handled broader engineering oversight. They faced an obvious problem immediately: building over open water repeatedly for miles. Traditional bridge construction moved slowly, piece by piece. This project couldn't afford that pace. So engineers designed something deliberately simple instead: a repeatable structural unit used constantly. 2 concrete piles driven into the lakebed, a bent cap connecting them together. That cap supported the ends of 2 deck sections, each deck section spanning 56 feet. This basic unit repeated continuously across the entire crossing, same pattern, mile after mile. Simplicity mattered enormously here for one specific reason: identical parts could be mass-produced. If every piece looked the same, workers could build faster, much faster than custom construction allowed. This approach borrowed directly from factory production methods, assembly lines essentially applied to bridge building. Nobody had attempted this specific approach before, not at this scale, not over water. If you're enjoying this story, hit subscribe. We cover engineering feats regularly. The design itself solved part of the challenge. Speed still needed serious additional planning though. Building identical parts meant nothing without producing them fast enough. Volume mattered just as much as design. 24 miles required thousands of individual components, piles, caps, and deck sections everywhere. Manufacturing each piece individually on site would take far too long. A different method was needed. Engineers decided to build a dedicated production facility instead, somewhere close to the construction site. This facility would essentially manufacture bridge parts continuously, like a factory running non-stop. Workers there would produce piles, caps, and decks repeatedly, identical pieces ready for installation. Getting finished pieces from a factory to open water presented its own problem, though. You can't drive a 56-foot concrete deck section across a lake by truck. Water transportation seemed like the obvious answer here. But nobody had tried this before. Successfully combining mass production with water-based delivery would prove genuinely groundbreaking. If it worked, everyone involved understood the stakes clearly. Failure here meant missing that 23-month deadline entirely. Success, though, could mean something historic. The fastest major bridge ever built. A simple design was step one. Building thousands of identical pieces fast enough was step two. Workers built a concrete casting plant at the bridge's northern end. This plant became the heart of the entire operation, genuinely continuous, factory-style production. Piles, bent caps, and deck sections all came from here. Identical, repeatable, ready for shipping. One engineer, Dr. Maxwell Upson, solved a critical problem early. Standard piles wouldn't work here. Existing piles typically measured 24 inches or smaller in diameter, too weak for this project. Upson developed something considerably larger instead, 54-inch hollow concrete piles, dramatically stronger. These piles used a specific manufacturing method called Kenviro. Centrifugal force shaped the concrete. This process created denser, drier concrete than typical methods allowed. Strength reached 10,000 0. That strength mattered enormously given what these piles needed to support. Decades of traffic, constant weather. Once cast and cured, finished pieces needed transportation to their final locations. Trucks couldn't drive 24 miles across open water. Workers needed a different solution entirely. Barges became the answer. Flat, stable platforms capable of carrying heavy concrete sections. Workers loaded finished piles, caps, and deck sections directly onto waiting barges. These barges then carried components out across the lake itself, toward their installation points. Picture the choreography this required constantly. Production, loading, transport, installation, repeating endlessly. Every single day the cycle needed to function smoothly. Any delay threatened the entire timeline. Workers driving piles into the lake bed needed materials arriving precisely on schedule. Too slow, and installation crews sat idle, wasting valuable time. Too fast, and materials piled up unused. Coordinating this balance across 24 miles represented genuine logistical achievement. Few projects attempted anything comparable. This wasn't traditional construction happening at one fixed location. This moved constantly, methodically, across open water. Assembly line thinking applied directly to civil engineering. The first time anyone had tried this, previous bridges, however large, hadn't used mass production this systematically. This changed that completely. Standardized components meant crews could work with genuine speed and confidence. Nothing custom, nothing improvised. Every pile matched the last. Every deck section matched too. Consistency enabled real velocity. This approach paid off dramatically once construction reached full momentum. Progress accelerated week after week. What might have taken years using traditional methods instead moved remarkably fast. The plan worked. What it produced was the fastest 24 miles of bridge anyone had ever built. 24 miles, built almost entirely over open water. Assembly line methods never tried before. Workers proved mass production could work beyond factories, even across an entire lake. The causeway still holds its record today, still crossing water nobody else has matched. If you enjoyed this story, hit subscribe for more construction history.